Hello everyone. So this is the fourth video in the series of videos talking about the Myhill-Nerode theorem and DFA minimization. So let's recap what we discussed last time. So last time we saw a central theorem in the discussion of finite automata, namely the Myhill-Nerode theorem, which gives a characterization of regular languages. In particular, we defined an equivalence relation R sub L for any language L, and this is an equivalence relation over strings over strings on an alphabet sigma, defined with respect to any language L. And then what we showed is that any language L which is regular, for such a language, the relation R sub L has finite number of equivalence classes. And if a language is not regular, then R sub L will induce infinite number of equivalence classes. And as a corollary, during our proof, like in the course of our proof, we also saw a very interesting fact, namely that given any regular language L, if you're thinking about just regular language L, then not just that the relation R sub L has finite number of equivalence classes, but it also, the number of equivalence classes in R sub L is also exactly the same as the minimum DFA computing the language L. By minimum DFA, I mean the DFA which computes the language L is regular, so there must be a DFA which computes, which recognizes that language L. I just mean, when I say DFA computes the language L, I just mean the language of the DFA is L. So think of the space of all such DFAs. And then what we saw is that the minimum, by minimum DFA, we mean the DFA with the fewest number of states, with the smallest number of states which computes this language. So R sub L has this very interesting thing that the number of equivalence classes in R sub L is exactly the number of states in the smallest DFA for the language. Now, while the Myhill-Nerode theorem does give us this characterization, or the proof of it does give us this characterization, it doesn't tell us how to compute the smallest DFA. How, like if I'm given a regular language, how can I compute the best DFA, the smallest DFA for the language? And one way you should think of such a thing is that the DFA of the, one way you should think of this kind of a DFA, sorry, just a second. So one way you should think of this as computing the smallest DFA. What does that mean? The small, in general, when you're thinking of a language is a proxy for general computation. And if you think of restricting yourself to the class of programs which are captured by a finite DFA, then what we are going to see in today's lecture, what we are going to see in this video rather, is the way to compute the best program for this language. If instead you were to think about general programs, then later in the course, you will see how that is finding the best program computing a language when you do not just think of finite DFAs for the program, but also like arbitrary programs, let's say C programs or something, then a similar algorithm is provably impossible. Anyway, that was just a recap of what we discussed last time. So the aim of this lecture is to prove the following theorem. In particular, we will give an algorithm which, when given a DFA M, so if I present a DFA to you, let's call it M, it will output another DFA M prime, whose language will be same as that of M. And further, among all the DFAs whose language is L, M prime will have the fewest states. So in particular, it's an effective version of the non-constructive thing I mentioned earlier. It's giving an algorithm to compute the smallest DFA for a regular language L, where the regular language L is being presented to us through a DFA computing the language. So this will be the goal for this video. And I'll just say that, you know, as we'll see, our algorithm for this problem will run in time polynomial in the description size of M. So M is presented to you as a DFA, so you can think of it as presented to you as a graph. And the running time of our algorithm would basically scale polynomially in the number of states and the alphabet, which is also a proxy for the size of the representation or the description size of the DFA. And in fact, one can do better and achieve nearly a linear time algorithm for DFA minimization. By a nearly linear time algorithm, I mean that it will basically run in time nearly linear in the description size of the DFA. However, we will just focus on the simpler algorithm because running time is not the main thing that we want to focus on. And in fact, I just mentioned this at the beginning, that our algorithm will be running in time polynomial in the description size of the DFA. And again, the description size of the DFA just means the number of states, how many bits you require to represent the DFA, which is the number of states plus the size of the alphabet effectively. So, but while our algorithm will be efficient, for most of this discussion, I will basically ignore any discussion of the running time. If you care about it, then you can just we can just go through the steps and you'll find out that the running time of our algorithm is polynomial in the description size of the DFA. Okay. So maybe unsurprisingly, given how fundamental a role equivalence relations have played in the context of Myhill-Nerode theorem, let's discuss one more equivalence relation, okay, which will be very useful in the context of DFA minimization. So suppose I give you a DFA M, okay, and remember the goal is that I want to produce another DFA M prime with the same language as that of M, but whose the number of states in M prime should be the fewest among all the DFAs computing L of M. So suppose M is this DFA, so that's what I'm trying to do. Now in this context, I define an equivalence relation RQM. Okay, RQM is an equivalence relation on the states of the DFA M. On the states of the DFA. This is unlike R sub L and R sub M we saw in the previous video, which were equivalence relations on strings. RQ comma M is an equivalence relation on the states of the DFA. And how is this equivalence relation defined? Well, we say P comma Q is in RQM if for all strings Z in sigma star, if the following holds, if you start from P and read Z and you start from Q and read Z, either both the times you will reach an accepting state of a state in F, or both the occasions you will reach a state not in F. So if for every string Z, it is the case that when you start from P and you start from Q, you either reach an accepting state or you reach a rejecting state, a non-accepting state, then we say P comma Q is in RQM. Okay. It is easy to verify that RQ sub comma M is an equivalence relation. Well, reflexivity is trivial because, of course, P comma P by definition is an RQM for any P. It is also clear that the relation is symmetric because our definition makes no distinction between P and Q. Their roles are reversible. And finally, again, it's easy to verify that RQ comma M is also a transitive relation. That's because if P comma Q is in RQM, then you know that when you read a string Z from P and Q, you reach either, in both cases, you reach an accepting state or rejecting state. And likewise, if little q comma R is also in RQM, then you know that again, if you start from Z and you if you read Z, start from Q and start from R, you either reach an accepting state or you reach a rejecting state on both occasions. And then this implies that if you read a string Z, then from both P and R, you either reach an accepting state or rejecting state, implying that P comma R is also in RQM. So this relation is easily verified to be an equivalence relation. And again, the proof was trivial basically by definition, as has basically been all the proofs of equivalence relations we've seen so far. Okay, so now that we have defined what the equivalence relation RQM is, let me make give another definition. Namely, we say that whenever P comma Q is not in RQM for two states P and Q, we will say P and Q are distinguishable. You should also recall that in the previous video, we gave a definition for distinguishing two strings with respect to a language L. We said two strings X and Y are distinguishable with respect to L if when you append Z at the end of both of them, there exists a choice of Z such that one is accepting and another one is in the language and another one is not in the language. So this is a definition of distinguishability with respect to states and not strings. So let's remember that. Whether we are talking about states or strings will be clear from the context. So now the first thing to observe is that while we have defined the equivalence relation RQM and we proved it's an equivalence relation, it is not obvious from the definition that if I give you a finite automata M, how do you compute the equivalence relation RQ, M? Let me be a little more precise. So the definition of RQM, recall, is that two states P and Q are in RQM if for every string of any length, it is the case that when you start from P and start from Q and you read Z, you either reach an accepting state on both occasions or the rejecting state on both occasions. But say if I give you P, P and Q and I ask you, are they in RQM or are they not in RQM? How will you verify such a thing? Because by the definition, you have to go over every string. There are infinitely many strings and make sure that conditions 1 and 2 hold for every choice of Z. How could you potentially, so then it seems like, while it's well defined, it's not clear how given P and Q and the description of an automata M, how can you tell me whether P and Q are in RQM or not? And what we are now going to do is to give an algorithm to do this. And in fact, the way we will give an algorithm is that we'll define, in fact, not one equivalence relation, but we'll define a hierarchy of equivalence relation. For every integer j greater than or equal to 0, we will define an equivalence relation RQ, M, J. Okay, and this will be related to RQ, M as the name suggests. And there's a typo here, but the thing is that as we'll see, the hierarchy of the reason we are calling these sequence of equivalence relations as hierarchy of relation is that whenever j is greater than or equal to k, the equivalence relation RQ, M, J will be a refinement of RQ, M, K. So as you go higher and higher up in the hierarchy, the equivalence relations will refine each other. There will be successive refinements. So now let me define what an equivalence relation, what RQ, Q, M, J is. So let's start with what RQ, M, 0 is. So two states P, Q are said to be in RQ, M, 0 if either both are accepting states or neither is. An instructive way to think about RQ, M, 0, even though the definition is very simple, is that first of all, observe what RQ, M, 0 is doing is that it's taking all the states and partitioning it into two parts, the accepting states and the non-accepting states. But one way and a suggestive way to say what we're doing here is that whenever P, Q can be distinguished by strings of length 0, and remember there's only one string of length 0, that's the empty string, then P, Q are not in RQ, M, 0. So P and Q fall in different equivalence classes. What do I mean by being distinguished by strings 3 of length 0? So remember, when we're defining the equivalence relation RQ, M, then we said, suppose I tell you P, Q is not in RQ, M. What does it mean? It means there's a string Z which distinguishes between them. By distinguishing between them, I mean that you start from P and you read Z and you start from Q and you read Z. Then in one case, you will go to an accepting state, and the other you will go to a rejecting state. So that's what we mean by a string Z distinguishing between P and Q. And what RQ, M, 0 is saying that two states P, Q is not in RQ, M, 0 if they can be distinguished by a string of length 0. Namely, if you read the empty string, then one ends up in an accepting state, the other is not in an accepting state. Okay, so that's one way to think about RQ comma M comma 0. On the other hand, now now that we have seen the definition of RQ comma M comma 0, let me just mention why our choice of nomenclature. Namely, observe that P comma Q is an RQM, the equivalence relation we defined here. When you say P comma Q is an RQM, it means doesn't matter how long a string V you choose, P and Q cannot be distinguished. Okay, so that's what RQ comma M is. It's basically, so RQ comma M comma 0 is being distinguished by string of length 0 if P and Q is not in RQM. RQ comma M, when you say P comma Q is in RQM, you mean that they cannot be distinguished by string of any length. And now we arrive at the definition of what RQ comma M comma J is, which is basically like interpolates between RQ comma M comma 0 and RQ comma M. So we say two states P comma Q is not in RQ comma M comma J if either they are not in RQ comma M comma J minus 1. So two strings which are in different equivalence classes in RQ comma M comma J minus 1, they are now automatically in different equivalence classes with RQ comma M comma J, or there exists a symbol sigma such that P on reading sigma goes to P prime, Q on reading sigma goes to Q prime, and P prime comma Q prime are in different equivalence classes with respect to the J minus 1th equivalence relation, RQ comma M comma J minus 1. So you are saying that P comma Q is not in RQ comma M comma J if either it's not in RQ comma M comma J minus 1, or you can read a symbol sigma, a common symbol sigma, and go to the states which are now not in RQ comma M comma J minus 1. Another way you can just verify this is true, just follows by the inductive definition of RQ comma M comma J, is that when you think of P comma Q is not in RQ comma M comma J, it means that there exists a string V of length J or shorter such that P reaches a final state on reading V and Q does not, or vice versa. Okay, and you can check that like this interpretation. So this interpretation is easy to see from the definition of equivalence relation RQ comma M comma J, because what we are saying is that either P comma Q is not in RQ comma M comma J if it's already not in RQ comma M comma J minus 1, or you read a symbol sigma, and then you are in two states which can be distinguished in RQ comma M comma J minus 1. And so naturally, this leads to this interpretation of RQ comma M comma J. Now, two things I want you to observe. The first thing is that trivially, this refinement fact that I mentioned, that RQ comma M comma K refines RQ comma M comma J whenever K is bigger than J. This immediately follows from the definition now. And this is because observe that whenever, by definition, whenever two states are in different equivalence classes with respect to RQ comma M comma J, they are also in different equivalence classes with respect to RQ comma M comma J plus 1, and hence inductively in every RQ comma M comma K for K bigger than J. So RQ comma M comma K is a refinement of RQ comma M comma J for any K greater than equal to J. And the second thing you should observe is that RQ comma M, you should essentially, I'm not writing this in a precise sense, we'll make this precise very soon, but you can think of it as like, that if you think of the equivalence relation RQ comma M comma J and let J be very, very large, arbitrarily large, then you will get RQ comma M, right? Because RQ comma M comma J is just saying, can P and Q be distinguished by a string of length at most J? RQ comma M says, can P and Q be distinguished by a string of any length? So As you choose larger and larger j, you're allowing for the distinguishing string to become larger and larger. And hence, once you take j to be essentially like in infinity, then rq comma m is you obtain rq comma m. Again, this is not a precise mathematical statement. So this was just to give you an intuitive idea, this limit statement that I made. This is just to give an intuitive idea. But now we will make this concrete. We won't have to take any limits of anything, but this was just to give you an intuitive idea of what's going on. So, okay, we have defined rq comma m comma j, these equivalence relations. Okay. And now how do we compute these equivalence relations? And if we manage to compute rq comma m comma j for any j, how does it give us rq comma m? Well, so first of all, observe that the equivalence relation rq comma m comma 0 can be computed in polynomial time, because that equivalence relation only has two equivalence classes, the accepting states and the rejecting states. So that equivalence relation is easy to compute. In fact, it can be computed in polynomial time. Secondly, the next observation is that if I give you the equivalence classes corresponding to rq comma m comma j minus 1, then there is a polynomial time algorithm to compute the equivalence relation rq comma m comma j. Because the reason is that if we are trying to decide if two states should fall in equivalence relation rq comma m comma j, or rather they fall in different equivalence classes, then you have to first see, hey, are they in different equivalence classes with respect to rq comma m comma j minus 1? If yes, then you're already done. Otherwise, you can just go over every symbol sigma, see what state you go to when you start from p and read sigma. Likewise, you start from q and read sigma, see what state you go to. And if any of these p primes comma q primes are in different equivalence classes for rq comma m comma j minus 1, then again p comma q will be in different equivalence classes. Since you can iterate over every pair p comma q and every symbol sigma in in time size of q squared, so the number of states squared, one for each p and q, times symbol of sigma. And then for each of these things, you can check whether either conditions 1 or 2 hold. Then that means that if you have been given rq comma m comma j minus 1, you can obtain rq comma m comma j in polynomial time. So given rq comma m comma j minus 1, you can obtain rq comma m comma j in an additional polynomial time. So this means that given any j, I can compute the equivalence relation rq comma m comma j. And the running time would be polynomial in the number of states, the alphabet size, and j, because for each going from j minus 1 to j, the number of going from j minus 1 to j, you will always incur an additional polynomial time. Okay. So now we make yet another crucial observation. Namely, whenever rq comma m comma j equals rq comma m comma j plus 1, then rq comma m comma k equals rq comma m comma j for all k greater than equal to j. What is it saying? It's saying that if there are two successive equivalence relations in this hierarchy which are same as each other, then every equivalence relation after that in this hierarchy is the same. How do we prove this? Well, again, it's a very easy proof by induction. Observe that it just suffices to show that rq comma m comma j plus 2 equals rq comma m comma j plus 1 under our hypothesis, because once this is true, then we can just inductively get rq comma m comma j plus 3 equals rq comma m comma j plus 2, which is the same as rq comma m comma j plus 1, which is the same as rq comma m comma j. So we can just apply this inductively. So it just suffices to show that rq comma m comma j plus 2 equals rq comma m comma j plus 1. Okay. So to show this, suppose I consider p comma q which is not in rq comma m comma j plus 2. Well, there are two possibilities by definition. Either p comma q is also not in rq comma m comma j plus 1. Well, then this pair has the same status vis-a-vis the equivalence relation RQ comma M comma J plus 1 and J plus 2. So then we are done. Or else, if P comma Q is not in RQ comma M comma J plus 2, then there exists a symbol sigma such that starting from P and reading symbol sigma, you go to P prime, and starting from Q and reading symbol sigma, you go to Q prime, such that P prime comma Q prime is not in RQ comma M comma J plus 1. But observe that by our hypothesis, RQ comma M comma J plus 1 is the same as RQ comma M comma J. So P prime and Q prime will also be in different equivalence relations, different equivalence classes with respect to RQ comma M comma J, which would have meant now that these would be in P prime comma Q prime. Since P prime comma Q prime is in RQ is not in RQ comma M comma J, it would also mean that P comma Q is not in RQ comma M comma J plus 1. Okay, so that would imply that again P and Q have the same status with respect to equivalence classes in RQ comma M comma J plus 2 versus RQ comma M comma J plus 1. Thus we get that RQ comma M comma J plus 2 equals RQ comma M comma J plus 1 equals RQ comma M comma J, thus finishing the proof. Okay, so upshot of the story here is that whenever two equivalence relations in this hierarchy, two successive equivalence relations in this hierarchy become equal, then they continue to stay equal for the rest of the hierarchy. And now this tells us something very important. This tells us that RQ comma M comma N equals RQ comma M. Okay. This tells us that actually we will now see why this is true. This tells us now that whenever to compute RQ comma M, you just need to compute up to RQ comma M comma N. That also implies automatically, I will prove this claim, but that also automatically implies that you can compute the equivalence relation RQ comma M in polynomial time, because you can compute RQ comma M comma N in polynomial time. And I should say N is the number of equivalence classes actually N is the N is the number of states in Q. Okay. Okay, how do we prove this claim? Well, the reason this claim is true is that note that RQ comma M comma J is a refinement of RQ comma M comma J minus 1. So the number of equivalence classes as we go up the hierarchy can either stay the same or increase. Okay. Whenever now what happens? Suppose you are going from RQ comma M comma J to RQ comma M comma J plus 1. Either RQ comma M comma J plus 1 equals RQ comma M comma J, or RQ comma M comma J plus 1 non-trivially refines RQ comma M comma J. If they are not equal, if RQ comma M comma J is not equal to RQ comma M comma J plus 1, then RQ comma M comma J plus 1 is a non-trivial refinement of RQ comma M comma J, meaning that the number of equivalence classes in RQ comma M comma J plus 1 is at least 1 larger than the number of equivalence classes in RQ comma M comma J. Now, observe this is an equivalence relation on the states of the DFA. So you cannot have more than n equivalence relations. There are more than n equivalence classes. So this means that either within n steps, the number of equivalent, either like as we go from RQ comma M comma 0 to RQ comma M comma 1 to RQ comma M comma 2, so on, either within the first n steps at some point two successive classes two successive equivalence relations are the same, and then you know that there is nothing more up the hierarchy, or you arrive at the thing that each time a new equivalence class is created. But since you cannot have more than an equivalence classes, then hence this thing must terminate by rq comma m comma n. So thus in either case, whether the process, either case doesn't matter what happens, by rq comma m comma n, the process is certainly stopped. So rq comma m comma n plus 1 equals rq comma m comma n equals rq comma m comma n plus 2, and so on. Okay. And now what would this mean? That means that you're getting that any string, this now implies that you don't need to go to if two strings p and q, sorry, if two states p and q are distinguishable by any string z, then they are distinguishable by a string of length n or smaller, thus implying that rq comma m comma n equals rq comma m. So again, I'm just saying that now this definition makes sense, because to get rq comma m, basically we had to go to rq comma m comma j for arbitrarily large j. But the point is that one doesn't need to go to arbitrarily large j, because the process of creation of successive equivalence classes stops by the time j reaches n. So thus, in this manner, we can compute the equivalence relation rq comma n. Let's now move to DFA minimization. So now that we have defined the equivalence relation rq comma m, sorry, this should be rq comma m. Now that we have defined the equivalence relation rq comma m, let's now talk about DFA minimization. So given the equivalence relation rq comma m and the DFA m, we are going to now construct a DFA, a different DFA for m, a different DFA for L of m, as follows. Let k be the number of equivalence classes in rq comma m. We will assign for each equivalence class in rq comma m, we will assign a state in the DFA. Okay. So let q bracket m comma q denote the equivalence class of q in the equivalence relation rq comma m. So this should have been rq comma, this should have been bracket, this thing should have been, I could have written it as bracket q comma m. This was a typo, I wrote it as m comma q, but it's immaterial. So for a state q, bracket q m comma q, let it denote the equivalence class of q in the equivalence relation rq comma m. We will now construct an automata as follows. We will, in q prime, will have a state corresponding to each of these equivalence classes q bracket m comma q. The starting state of the DFA would be the equivalence class of the starting state of the original DFA, which is equivalent q naught. So the starting state of the new DFA will correspond to the equivalence class of q naught. The final states of the new DFA will correspond to the equivalence classes corresponding to the final states of the old DFA. The transition function is again will be defined as, if you are in the state corresponding to the equivalence class of m comma q and you read a symbol sigma, you will go to the equivalence class of the state corresponding to delta q comma sigma. And our final automata construction will be m prime, which is q prime sigma delta prime q naught prime f prime. So one thing we should make sure is that our definition is meaningful, as in it's well defined. What does it mean? Well, our definition is as such well defined, except potentially for the transition function. This consideration again arose, if you remember, in the proof of the Myhill-Nerode theorem as well. So when I say I have to show that the definition is well defined, I mean that what we have to show is that if you start with two equivalence classes which are the same, meaning suppose qm comma q equals rm comma q, the equivalence classes are the same. So q and r fall in the same equivalence class with respect to the equivalence relation rq comma m. Then we want to show that this transition function is well defined in the sense, if you read symbol sigma from Q and read symbol sigma from R, you go to states which are continue to be in the same equivalence relation. Only if this happens is this definition of the equivalence relation, of the transition function well defined. Okay. And to see why this is true, you should just refer to our construction of the equivalence relation MQ, of the equivalence relation RQ comma M. Namely, suppose Q and R were in the same equivalence relation class, but delta Q sigma and delta R sigma were in different equivalence classes, then the way we constructed this, our algorithm for constructing the equivalence relation RQ comma M would have put Q and R in different equivalence classes, because once delta Q comma sigma and delta R comma sigma, hypothetically, if they were in different equivalence classes, then on reading a symbol sigma from Q and R, you are reaching these states which are different equivalence classes. Then by definition of RQ comma M, Q comma R should also be in different equivalence classes, which they're not. Which means that if Q M comma Q equals R, the equivalence class of Q and R are same with respect to RQ comma M, then the equivalence class of delta Q sigma and delta R sigma are also the same with respect to the this equivalence class, equivalence relation. Another quick observation we should make is that if Q is an accepting state, then any equivalence relation, any state which is in the same equivalence class as Q has to also be an accepting state. And this is just follows from the fact that RQ comma M refines the relation RQ comma M comma 0. Okay. In other words, two different accepting states might be in different equivalence classes, but if two accepting states, if there are two classes, two states in the same equivalence class, and one of them is an accepting state, then the other is also an accepting state. And same for rejecting states. So now that we have defined the DFA M prime, we now need to show that its language is the same as M. And this is again kind of follows easily. Namely, recall by a definition of transition function, if you start at the state corresponding to the equivalence class of P and you read sigma, then you go to the state corresponding to the equivalence class of delta P comma sigma. This is our definition of the transition function. So now suppose an automata M on input P, on input X, takes a state P to state Q. Then it is not hard to show that the automata M prime on input X, if it starts with the equivalence, if it starts with the state corresponding to the equivalence class of P, it will go to the state corresponding to the equivalence class of Q. Okay, this is just an easy proof by induction. Okay, you can just prove this by induction. Okay, this is not hard to show. Let me just say this is proof by induction, basically similar to the proof of by induction in Myhill-Nerode theorem. In particular, what is this, summarizing this thing, what it says is that if you suppose X is an accepting string, suppose X is an arbitrary string, if the original automata M starting from the start state Q naught takes it to a state Q, then the new automata M prime starts from the state corresponding to the equivalence class of Q naught and takes it to the equivalence class of Q. But this immediately implies that if X is in L, then it means that Q is an accepting state, and thus the equivalence class of Q MQ. So this state Q bracket Q M comma Q is an accepting state in the DFA M prime. Vice versa, if X is not in L, then Q is a non-accepting state, which means bracket Q M comma Q is a non-accepting state in the DFA M prime. So thus you get that if X is in L, then M prime accepts X. If X is not in L, M prime does not accept X, thus showing that L equals L of M prime. So by this, we have given any DFA M, we have constructed this different DFA M prime which accepts the same language as M. So only one thing remains to be shown is that this has as few equivalence classes as any DFA computing L of M. How do we show that? Well, let us count the number of states in M prime. Okay, we'll essentially count the number of states in M prime. So what do we do? So suppose you take suppose you take the state corresponding to the equivalence class of Q. Okay, so this square bracket Q M comma Q. Well, let us assume that it is reachable from the state corresponding to Q naught. Okay, let us assume that there is some string which starts from the equivalence class Q naught, reads Z and goes to QMQ. If this state QM comma Q is not reachable, then you can anyway discard such a state and it will not affect the DFA. So without loss of generality, I can assume that all the states bracket Q, M comma Q, they're all reachable. Okay. So if there's such a state, then let ZQ, if the state Q equivalence class of Q is reachable from the equivalence class of Q naught, then let ZQ be a string which takes the initial state of M prime to reach the state bracket QM comma Q. Now what I'm going to argue that corresponding to if two states in M prime are different, namely QM comma Q is not equal to PM comma Q, then the two strings ZP, which starts from the initial state and takes the automata M prime to bracket P M comma Q, and the string ZQ, which starts from the initial state of M prime and takes it to bracket Q M comma Q, those must be distinguishable strings. And by distinguishable strings, I just mean that ZP comma ZQ is not in RL, where L is the language of M. Well, why is this true? Well, note that Q comma P are in different equivalence classes with respect to Rm comma Q. What does that mean? That means that there's this input Z star, okay, such that Q goes to a state if you start from Q and read this input Z star, you go to a accepting state, and if you start from P and you read the input Z star, you go to a state not in F, or vice versa. Okay, so without loss of generality, let's assume this is the thing which happens, that you start from, there's an input Z star such that Q starts from, on starting from Q and reading the string Z star, you go to a state in F. On starting from P and reading the string Z star, you go to a state not in F. Well, but starting from the initial state and reading ZP would take you to Q, would take you to P, and starting from the initial state and reading ZQ would take you to Q, which means that if you read the string ZQ Z star, you will land, it will be a string which will, the DFA would read the string ZQ Z star and go to an accepting state, and the DFA M would read the string ZP Z star and go to a rejecting state, a state not in F, which would mean that ZQ Z star is in LM and ZP Z star is not in LM. Thus means that ZP comma ZQ is not in RLM. In other words, corresponding to every state in the DFA M prime, we have identified a string such that all these different strings are in different equivalence classes with respect to R sub LM. In other words, we have at least as many equivalence classes in RLM as the number of states in M prime. In the previous lecture, we had seen that any DFA computing LFM must have at least as many states as the number of equivalence classes in RLM. So this shows that the DFA we have constructed has precisely the smallest number of states that any DFA computing L of M can have. This finishes the proof showing that our DFA that we have constructed has the fewest number of states corresponding among all the DFAs computing the language. So let me conclude here. Thank you.